Hello and welcome to Joey's AP Precalculus, Lesson 1.4. In Lesson 1.4, we will be looking into polynomial functions and the rates of change. We're now finally moving on from quadratic functions and we're learning about polynomial functions now. Let's look at the lesson objective. We only have one lesson objective proposed by College Board today, which is identify the key characteristics of polynomial functions related to rates of change. We're going to look into the key characteristics of polynomial functions. So what are these key characteristics? I have divided the key characteristics into three parts. The first part is the components of a polynomial function. The extrema of a polynomial function is the second one. And the concavity of polynomial function is the third one. So we'll be looking into all three characteristics of polynomial function, and I've divided as 1a, 1b, and 1c. So let's look into it. Let's first look into lesson objective 1a. We're going to look into the definition of polynomial as we're looking into polynomial functions. So the definition of polynomial is a finite sum of terms of the form ax to the power of n, where a is a real number and n is a whole number. Okay, so polynomials are basically sum. So we keep adding like a term that has this format. So it's simply like something like this. We keep adding a term that is in this format. Some of the important things you have to know: a polynomial's coefficient, which is basically a number attached to the variable, should be a real number. So this number attached should not be an imaginary number. As you can see from this example, you can see that all coefficients are real numbers. They're 8, -5, and 6, right? So like this, all coefficients, or basically the number multiplied to the variable, should be a real number. One more thing important is the n, the exponent, should be a whole number. The definition of a whole number is natural number plus 0, right? What are natural numbers? They're like positive numbers that are not like fractions or decimals, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are natural numbers, and including 0. So these are whole numbers, okay? So basically, a polynomial should be the sum of terms in the format of ax to the power of n, and a should be a real number, and n should be a natural number. N should be a whole number, okay? So just recap. Let's look at this example. The number attached to variables are called coefficients. The variables are called variables, of course. And if there's just a number without a variable, that is called constant. Okay? Let's move on. Oh, I forgot to explain finite. Finite sum means that there is an end. Infinite sum means that there isn't an end. It means that we keep adding stuff. But all polynomial function has to have an end. For example, for this example, they're only adding 3 terms. So it is a finite sum. There is an end of a sum. So all polynomials should be a finite sum, okay? Let's look at some more vocabulary words that we must know, which are leading coefficient, degree, and leading term. I'll read the definition real quick. A polynomial is written in standard form when the values of the exponents are in descending order. The degree of the polynomial is the value of the greatest exponent. The coefficient of the first term of a polynomial in standard form is called the leading coefficient. I'll explain this by looking at this kind of like a chart below, okay? So let's look, they're given a various examples, right? Let's look at the cubic example, okay? So this cubic function has 4 terms, right? So it is a finite sum with 4 terms being added to each other. Let's first look at the definition of degree. The dictionary definition here says that degree of a polynomial is the value of the greatest exponent. If you take a look at that, the first term has a exponent of 3. The second term has the exponent of 2. The third term has an exponent of 1. And the last term has an exponent of 0. Why? Because x to the power of 0 is equivalent to 1. Okay. So basically, if you take a look at this, what's the highest exponent term? It is 3, right? So we're saying that the degree of this entire polynomial is 3. Okay. Leading coefficient is basically the coefficient attached to the variable that has the greatest degree or the greatest exponent. So for this example, 8 is attached to x to the power of 3. That's why the leading coefficient is 8. 12 can never be a leading coefficient for this example because the exponent of the second term is less than the exponent of the first term. Okay. Hope that makes sense. One more vocabulary we have is leading term. Leading term is basically the term that has the leading coefficient. So for this example, 8x to the power of 3 has the leading coefficient, right? So we're calling this the leading term as well. Okay. Just a recap for general thing you have to know. What is standard form? Standard forms are basically form out where the first term has the highest exponent, second term has the second highest exponent. So all these examples are written in standard form. So why? Because the first term has the highest exponent, second term has the second highest exponent. So if something is written like 12x squared plus 8x to the power of 3, this is not written in standard form. Why? Because the second term has a higher exponent than the first term. Okay, hope that makes sense. So we look into several vocabulary words, including polynomials, leading coefficient, degree, and leading term. These are very important concepts and vocabulary words that you must know before learning polynomial functions, okay? One more thing we're going to learn is the condition of monomials. One thing you must know is all polynomial functions term are composed by monomials, right? I told you that polynomial is a sum of the term ax to the power of n, right? So something like ax to the power of n is called a monomial. So polynomials are basically sums of monomials, okay? So we learned two conditions of this monomial, right? We learned that a should be a real number and that n should be a whole number, right? There are some more conditions that you must know. So basically, a recap, monomial is a multiplication of a constant, which is a number, and a variable, right? We're going to look into some more conditions, which is the variables of a monomial cannot have a negative or fractional exponent. So this is an example of monomial. Monomial has an exponent, right? But one of the conditions is that the exponent can never be negative and can never be fractions. So if you look at something like x to the power of -2, this is not a monomial. So if a polynomial has something like a negative exponent, that is not a polynomial. Something like 3x to the power of 2 plus x to the power of -1 plus 8. This is not a polynomial because this is not a monomial. Why? There's a negative exponent. Same example, if we have a fraction as an exponent like this is also not a polynomial. When you're writing the reasoning, you should say that this is not a polynomial because the second term is not a monomial due to the fact that it has a fractional exponent. So these are the important kind of conditions that you have to know, that the variable should never be, the variable of a monomial can never have a negative or fractional exponent, okay? Having learned all these vocabulary words, let's solve some examples together. First example, determine whether c to the power of 4 minus 4 root c plus 18 is a polynomial. If it is a polynomial, state the degree of a polynomial. Okay. First, let's rewrite this. C to the power of 4 minus 4, c 1/2 plus 18. Yes, something square root is also the equivalent of c to the power of 1/2. The cube root is equivalent to c to the power of 1/3. Okay, so basically, because the second term has a root, if we change the format, it has a fractional exponent. So when we're writing the answer, we can say that no, it is not a polynomial. If we were to write the reasoning as the second term is not a monomial, the fact that it has a fractional exponent it is not a polynomial. So if you write like this as your reasoning, you'll get full credit. Okay. Let's look at the second example. Determine whether minus 16p to the power of 5 plus 3/4 p squared q to the power of 7 is a polynomial. If it is a polynomial, state the degree of a polynomial. So the coefficients are basically real numbers, right? They're not imaginary numbers. So let's give a check mark for the first condition. Let's look at the exponents. Are these whole numbers? Yes, they are. It does not have a fractional exponent or a negative exponent because it is a whole number, right? So this meets all the conditions of a polynomial. So we're going to say yes, it is a polynomial. But it asks you the second question as well. If it is a polynomial, state the degree of a polynomial. What is the degree? It is the highest exponent of a term, right? Okay, let's look at the first term. What is the exponent of this? It's 5, right? What about the second term? Oh, there's a mixture of two variables. The first variable has a degree of 2. The second term has a degree of 7, right? In this case, we're adding them. We're adding the two exponents. So it's 9. What is bigger, 5 or 9? 9 is bigger, right? So we're saying that the degree of this polynomial is 9. This is a very common mistake made by a lot of people. Because some people think, oh, 5 to 7. Oh, 5 is bigger. No, you have to take into consideration of both variables in a single term and have to add the exponents to derive the correct answer. Okay. Okay, determine whether x squared minus 3x power of negative 1 plus 7 is a polynomial. Okay, I told you that what are those conditions? The exponent should never be a fraction or a negative number, right? Oh, here's a negative number. So when we're writing the answer, we're saying no. And for reasoning, the second term as a negative exponent, showing that the second term is not a monomial. This would be a valid reasoning. Okay, let's look into example 4. State the degree and leading coefficient of 7z to the power of 3 minus 4z squared plus c. If it is not a polynomial in one variable, explain why. Okay, I didn't explain this concept, but what is polynomial in one variable? It's basically polynomial that has just one variable. For this example, the only variable given is z, right? So this is a polynomial in one variable, okay? What is the degree of this? What is the exponent of the first term? 3. Second term, 2. Last term, 1. What is the highest exponent? 3, right? So when we're writing the degree, we're saying that the degree is 3, right? I told you that the leading coefficient is the number attached to the highest exponent. So it would be 7, right? So we're saying that the highest exponent, sorry, the leading coefficient is 7. This would be the right answer. state the degree and the leading coefficient of 6a cubed minus 4a squared plus ab squared. If it is not a polynomial in one variable, explain why. So this is a polynomial, right? So we can write degree, right? Oh, wait, no, never mind. I just explained polynomial in one variable, right? If you take a look at this variable has a, this variable, sorry, this term has a, this term has a, but this term has a and b. So basically, this is not a polynomial in one variable. Why? Because the third term has a and b. The problem of this is we can't determine a clear degree and a leading coefficient. Why? Because the first term has a degree, the exponent of 3, so we can consider the leading coefficient as 6. But if you take a look at the third term, the exponent of this third term is also 3. Why? Because a has a hidden 1. So if we add 1 and 2, the exponent of the third term is 3, but the coefficient of the third term is 1. So the leading coefficient can be 6 or 1. So there's that kind of like confusion. So when we're writing the answer for this, we can just say that not a polynomial in one variable as the third term has both a and b as its variable. Okay, let's look at example 6. State a degree and leading coefficient of blah, blah, blah. If it is not a polynomial in one variable, explain why. So it only has x, right? So this is a polynomial in one variable. Let's look at the degree. What is the highest exponent? 6, right? The degree is 6. What is the number attached to x power of 6? It's -8. A lot of people write just 8. That is incorrect. You have to think of the sign as well and see if it is positive or negative. Okay. Good job. We're done with lesson objective 1A, which is learning the components of polynomial function. Now let's dive into 1B and learn about extrema. Okay, so there are two types of first I'll explain what extrema is. Extremas are basically minimums and maximums. We call this extrema because we think that these are extreme values, right? So basically minima and maxima are the extrema. There are two types of extrema, which are relative and absolute. The AP course, the framework also uses a term called global for relative. Sorry, my bad. Local for relative and global for absolute. So just think they're interchangeable terms. Relative extrema are the same as local extrema. Absolute extrema are the equivalent of global extrema. Okay. Let's look at the definition of relative and absolute extrema. Okay, let's first look at what is a relative minimum. Relative minimum of a function f is the greatest value f of x can attain on some interval of the domain. Okay, let's look at this example. They're given a polynomial function, right? If we take a look at only this interval, this is the highest point that the graph can achieve in this interval, right? However, what's the actual maximum? The actual maximum in the entire function is this, right? Because this point is higher than this. But we're still going to say that this is a relative maximum because this is relatively higher than other values in this interval, okay? So that's relative maximum, okay? Then what is absolute maximum? So absolute maximum, absolute maxima can be found by listing all the relative maxima and seeing what the highest is. So we have two relative maxima, right? What is bigger? What is higher? This is higher, right? So we're saying that f of b is the absolute maximum and f of a is the relative maximum. Same thing for relative minimum and absolute minimum. We're just looking at certain intervals. And if you take a look at this point is lower than closer points, right? So we're calling this the relative minimum. This is also a relative minimum because this is lower than the other points. But if you compare this and this, f of b is lower than f of a, right? So we're calling f of b as the absolute minimum, and we're calling f of a as the relative minimum. Think of it as what is like for relative maximum and relative minimum, think like, oh, it's relatively higher or relatively lower than the closer points. But for absolute, think it as the greatest maximum or the lowest minimum, kind of like that, okay? Okay, these are some important things that College Board wants you to know, okay? I'll read it. Where a polynomial function switches between increasing and decreasing or at the included endpoint of a polynomial with restricted domain, but the polynomial function will have a local or relative maximum or minimum output value. Of all local maxima, the greatest is called global or absolute maximum. Likewise, the least of all local minima is called the global or absolute minimum. Okay, so let's look at some things we know. I explained this, right? The greatest of all relative or local maxima is called the absolute maximum or the global maximum. The least of all local minima or relative minima is called the global or absolute minimum, right? So we know that part. But the first line is kind of something new. Another way of kind of approaching the concept of extrema is looking at whether the graph changes the increasing to decreasing or decreasing to increasing. We learned what the definition of increasing, decreasing constant is in lesson 1.1 as well as lesson 1.3, right? If you take a look at this graph, up till x equals a, the graph is increasing, right? But after it passes x equals a, it changes to decreasing, right? So you can also think of the concept of maxima or relative maxima as the point where the graph changes from increasing to decreasing. Same here. It is increasing till x equals b, but after it passes x equals b, it changes to decreasing. So you can also think of the concept of maxima as the point where graph changes from increasing to decreasing, okay? I'll write it here. By the way, maxima is the plural form of maximum. So if someone says maximums, that's incorrect. They should say maxima. Same for minima. The minima is the plural form of minimum. If someone says minimums, that's incorrect. They should say minima, okay? Same thing for minimas. If you take a look at this, it changes from decreasing to increasing, right? So we can say that this point is the relative or local minima. Same for this, decreasing to increasing. So we can call this point the minima point. Okay, so we basically also learned a College Board definition of some extremes. So we basically understood everything here, right? A polynomial function switches between increasing and decreasing. yeah, that's the extrema point. Regarding this that I'm highlighting in green, I'll explain this by solving some example problems together, okay? Second important thing that you must know according to College Board is between every two distinct real zeros of a non-constant polynomial function, there must be at least one input value corresponding to a local maximum or local minimum. What this is, I'll draw a picture or a graph for you. Okay, I drew a sample polynomial function. Okay, between every two distinct real zeros. So if you take a look at this, these are two distinct real zeros, right? What College Board is saying is that between these two distinct real zeros, there must be either a local maximum like this, or like for these two real zeros, there's a local minimum, right? So they're saying that between any two distinct real zeros, there must be either a maxima or a minima. I'll explain why this happens. Okay, so for a graph to become a zero, they should either increase or decrease while passing the x-axis, right? But for the graph to have another zero, for an increasing graph, they should decrease, right? You get it? That's why it changes from increasing to decreasing. So there is an extrema point. Same thing, for a graph that is above the x-axis to have a zero, they should decrease, right? But for that same graph to achieve another zero, it should switch from decreasing to increasing so that I can also touch the x-axis. So basically, you should know that if there are any two distinct real zeros, oh, there should be either a local maximum or local minimum, or relative maximum or relative minimum, okay? One last thing is that polynomial functions of an even degree will have either a global maximum or a global minimum. Okay. So, even degree functions. I hope you guys learned this in Algebra 2 or Algebra 1. But even degree functions are where the highest degree is an even number. Something like x to the power of 2. This is an even function. X to the power of 100. This is also an even degree function. One characteristic of an even degree function is its end behavior. What I mean by end behavior is that as x goes to positive infinity, y goes to positive, like, okay, let's say that as x approaches positive infinity, y also approaches positive infinity, okay? Then as x approaches negative infinity, y also approaches positive infinity. So there's some characteristics of even degree function is that regardless of the direction of x, like whether it goes to positive infinity or the negative infinity, the y direction is the same. So if I were to draw this, it's either having a shape like this or this. You get it? So although there might be some like squigglies, like still the two y directions at the ends are toward the same direction. What does that mean? It means that there is either a absolute minimum or a absolute maximum. Okay. For odd degree functions, on the other hand, they're either having the shape of this or this, right? So they might be having some relative maxima and minima, right? But they can never have an absolute extrema because the two ends are going towards the positive infinity and negative infinity, so it cannot have an absolute extrema. But for even functions, please note that they will have either a global maximum or a global minimum due to their nature of end behavior, okay? Without graphing, and you can immediately know whether they will have a global maximum or a global minimum because if we take a look at the leading coefficient, if the leading coefficient is a negative value, they'll have a shape like this. If the leading coefficient of an even degree function is positive, they'll be like this. So it'll be open up shape and open down shape, depending on the sign of a leading coefficient, okay? Let's look at some sample examples now, okay? Estimate and classify the extrema to the nearest 0.5 unit for the graph of f of x. Support the answers numerically and provide reasoning. Okay. Let's just point out some extrema. Extrema number 1, extrema number 2. Why? The graph switches from decreasing to increasing. And at this point, the graph switches from increasing to decreasing. Okay. So when we're writing the answer, we can say that there is a local or relative minimum of -8 at x equals, this looks like 1, right? -1, sorry. There is a local maximum. What's the corresponding y value for this? It's 12, and it's in the middle of 12 and 16, so it'll be probably like something like 14, right? 14 at x equals 2. When you're writing the minimum and maximum values, you must list its y value first, like this, and then you should write at x equals something. At x equals something. You should never write maxima or minima in a coordinate form. So if you say, oh, there's a relative maxima at like -1, -8, this is incorrect. You must list the y value first, like of something at something. Okay. You can disregard the x value, to be honest, but I recommend you do it. Okay. Okay, so this is the correct answer. They want us to support the answers numerically, so we have to make a table, right? This is related to the function rule we learned in lesson 1.1. So let's make a table. We just need few numbers, okay? Let's just do like -2, -1, 0, 1, 2, okay? When it's -2, it's corresponding to like something like 8. When it's -1, it's corresponding to -8, 0, 0, 1, it's like 4, 2, it's like 14, right? So we can support the answers numerically by providing reasoning, right? We can say that at x equals -1, the graph switches from decreasing to increasing, right? Same thing. You can say that for x equals 2. Oh, let's have one more, sorry. Let's have like 3, okay? So it's like 0. So we can also say that at x equals 2, it switches from increasing to decreasing. So if you explain this, the table that we made, like in words verbally, by providing reasoning in relation to increasing, decreasing, decreasing, increasing, you'll get full credit, okay? Let's look at example 2. Use the figure of y equals f of x at the right to answer these questions. First, what is the absolute maximum of f? Okay. Before, I told you that I'm going to explain the endpoints, right? When you're taking a look at the absolute maxima or the absolute minima, you should also take into consideration of these endpoints, because endpoints can also be extrema, okay? So what's the absolute maximum of f? It's this endpoint, right? Because this endpoint is the absolute maxima. No other points in graph exceeds this endpoint. So we're writing that the absolute maximum is 4 at x equals -4. At what x values does f have an absolute maximum? We wrote it here. x equals -4. What is the absolute maximum point on f? -4, 4. So the questions might ask you this, but when they're asking just like, what is the absolute maximum, make sure to write the y value first. And I recommend writing at something, okay? Okay, let's look at other questions too. What is the absolute minimum of f? Okay, it's here, right? But you should note that this is undefined. There's a point discontinuity. Then you're going to be like, oh, then what? Oh, then there's no absolute minimum, right? Right. So you're going to write does not exist. Why? Because the absolute minimum point has a point discontinuity. So you're writing does not exist. Second question, at what x values does f have relative minimum? These 2 points, right? So we're writing x equals -3 and x equals 1. Yeah, and I think I had a typo here. I think I meant maximum. For relative maxima, it's this point, right? So you're going to write x equals -1. So that would be the correct answer. Let's look into example 4. Determine whether the graph of f of x equals -2 x to the power of 8 plus x to the power of 3 plus 4 would have a global maximum, global minimum, or neither. I told you that an even degree function like this, 8 is an even number, right? So this is an even degree function, right? So this should either have a global or absolute maximum or absolute minimum, right? But because the coefficient of x to the power of 8 or the leading coefficient of this polynomial is a negative number, you should know that the shape overall end behavior will be somewhat similar to this shape, which shows that it will have a global maximum. The question does not ask you for reasoning, so you can just say the f of the graph of f of x has a global maximum. Okay. Is 94 an even number? Correct. Yes, it is an even number. The leading coefficient is positive, right? So without even graphing it, we can know that end behavior is something like this, right? So we should know that it has a global minimum. Example 6, 97 is an odd number, right? So we can say that the graph of f of x has neither a global max nor a global, min. Because the leading coefficient is a negative number, we should know that the overall end behavior will be something like this. Okay. Let's look into example 7. Understanding that the graph of y equals 2x to the power of 5 plus 4x cubed plus 2x squared has its x-intercepts at -0.4534 and 0. Determine the type of extrema that may exist in the interval -0.4534, 0. Provide reasoning as well. Okay. Okay, so for these kind of questions, we have to support the answers numerically. So we're going to determine whether the graph is showing an increasing or decreasing, and we're gonna determine whether the type of extrema at this point, okay? So these are quite hard and challenging questions, but it's also quite fun as well. So let's have -1. And instead of this hard number, let's just put -0.5, okay? And let's also have -0.25, 0, 0.5, and 1, okay? Let's plug these x values into this function to find the corresponding y value. So 2 minus 1 to the power 5 plus 4 minus 1 to the power 3 minus 2 minus, what is this? Minus 2 plus, sorry, minus 4 plus 2. So this would be -4, right? -0.5 is the equivalent of -1/2, right? So I'm going to write it like this. Plus, and then going to be something like this. I'll write the answer here. -1/16, -1/2 plus 1/2. This would be -1/2. Sorry, -1/16. Zero, 0. Let's do the easy stuff first, okay? And then this would be 2 plus 4 plus 2, so it's going to be 8. And then let's do 0.5 first, because that's easier than the terrible -0.25, okay? Okay, now let's do the terrible thing here. Okay, -0.25 is the equivalent of -1/4, right? Yes. And this FYI, if there's something like terrible questions like this, they're probably going to allow you to use a calculator. But I'm just going to demonstrate that it's also possible to solve these kind of questions without a calculator, just to demonstrate that it is possible. Okay. Okay. There's a terrible number. I hate this question. Okay. Uh, great. This would be great. Okay. Sorry for the delay, guys. Yeah, so to multiply 32. 31 over. Okay, great. Finally done with this terrible procedure, guys. We support the answers numerically, right? Okay, if you take a look at this, the graph is decreasing, right? So it's decreasing and then it's increasing, right? and then it's decreasing, and then it's increasing. But we just have to look at this interval, right? Sorry. Yeah. So because if you only look into this interval, guys, it switches from increasing to decreasing, right? From this interval. So we can determine the type of extrema as maxima or maximum, right? But because this is an odd function, it can never be a global maximum. So we're going to write relative maximum. And then we're going to provide reasoning. Is decreasing. Yeah, this would be correct. Okay, good job. Now we're in the final part, concavity. Okay, let's get started. So this is what I explained in the previous lesson, so I'm just gonna disregard it. Just think of it as if it has like a shape like this or this, it's concave up. If it's this or this, it's concave down. The definition of concavity is the change of the rate of change. Okay, I'm gonna write here. Great. In relation to concavity, we're going to learn a concept called point of inflection. What is the definition of point of inflection? It's the point of a graph where its graph changes its concavity. For example, in this graph, up till this inflection point, the graph is concave up. But after it passes that inflection point or the point of inflection, it changes to concave down. So this point is where the graph changes its concavity. So that's kind of like how you should know. Determine the points of inflection. Based on this point, the graph changes from concave up to concave down, right? So the answer for this example would gonna be 1, 0. They're asking for the point, so it is okay to write in coordinate form. Determine the points of inflection. This is, let's write, this is concave down, this is concave up, and then concave down, right? Am I right? I am right. Oh, then it switches from concave down to up. Isn't this point? No, this is an asymptote. This is an asymptote. So the answer for this would be none. Why? Because only the continuous portion of the graph is here, right? But the concavity of this part is consistent by being concave up. Same for these. There is a concavity change from this graph to this graph and this graph to this graph. But because it changes due to its asymptote, there is no point of inflection. Okay, let's look at this. This part is concave up. This part is concave down. This part is concave up. And this part is concave down. So the points of inflection are this, and this, because these are the points where the concavity changes. So it's going to be -1, -1, 0, 0, and 1, 1. Okay. Yeah, same thing. This is concave up. This has 0 concavity. This has concave up. This has concave down. And this has concave up. This is not a point of inflection because that is a point where the concavity changes to 0, so it does not technically change concavity. Same for this, it changes from 0 to concave up, so it does not count as points of inflection. So the correct point of inflection would be this point and this point. Great. Oh, we're done. Okay, let's go back to our first slide. So what we have learned today are basically the components of polynomial function, the extrema of polynomial function, and the concavity of polynomial function. Now, you can definitely say that you know all the characteristics of polynomial functions, and you can also solve some questions in relation to the rates of change. If you have any questions again, feel free to email me, and hope you had a fun and rewarding time today. Thank you, and bye-bye.